Good afternoon. Let me start module 5 today. So module 5 is digital electronics part that we'll be discussing from now on. So next 6 to 8 class, I'll be able to complete this module also. After this, I'll try to repeat from module 1. Okay, I'll try to revise. Okay, and also I'll try to solve few question papers. I think that will help you for the final exam. Okay, so let me start digital electronics basics, and then number system I will discuss. After that, I will talk about ones complement and twos complements, nines complement, tens complement, then Boolean algebra I'll be discussing in brief, Boolean laws, and then we'll discuss about logical gates, and then digital systems, few digital systems starting from simple adder, half adders, full adder, and then some digital systems like mux, demux, multiplexer, demultiplexer, and all. Finally, you have communication system for discussion. Okay, so that is about the module 5 what we have for discussion. So yeah, yes,
digital electronics ಐದನೇ ಚಾಪ್ಟರ್ ಹೋಗ್ಬಿಟ್ಟವ್ರೇನೆ ಯಾವ ಚಾಪ್ಟರ್ ಅವ್ರೆ ಅಂತಾನೆ ಗೊತ್ತಿಲ್ಲ ನಂಗೆ.
ಯಾರಪ್ಪ ಅದು? ಆಕಾಶ್. ಆಕಾಶ್, Akash.
Yes sir. Yes sir.
Any difficulty?
No sir.
Okay.
Sir,
so
sir,
tell me.
Sir, regarding that feedback, I have some doubts, sir.
Which feedback, man? Which feedback amplifiers you are talking?
Yes sir, yes sir.
After the class, last 5 minutes we'll discuss. Okay.
Sir, no problem, sir. I will call you personal and I will take.
Okay, no issue. So let me start this next 45 minutes. We'll try to complete some portion in this. So I'll start with the basics of digital electronics. To begin with, you have some signal representation. This is a signal representation for electric field of Earth is recorded over 12 months, and just it is represented. Nothing to worry, just I am trying to convey how message looks like, how you represent a signal. Maybe it is signal recorded, this signal is recorded for Earth's electrical field for 12 months period, and it is just displayed. So mainly this is to convey the data. Okay, so next you have many other electronic system where we try to convert a signal from one form to another, right? So we have one example I will take up. This public addressing system, you can observe here, what we can see is a signal coming from signal maybe in any form. The basically normally we get the signal in analog form. What I'm speaking, voice signal, it is acoustic signal that is sensed by your microphone, right? So microphone senses the voice signal and converts into electrical signal, and that electrical signal is fed to the amplifier. Actually, why? Because usually microphone sensed signal magnitude will be very less, in millivolts. Maximum you will get in millivolts, and that is not audible to the large gathering, right? So usually we use amplifier, and we magnify the signal strength, and then transmit it or send it to the loudspeaker output device. And output of speaker is also a sound signal, which can be represented in analog signal. Or analog signal, when I say, it is a continuous signal. Continuous signal means what? it is a signal which the value of signal defined for all time t, from 0 to infinity, or 0 to some period. It is continuously defined. In between, you don't have any discontinuity in the signal. So some signals I can represent this way. The one signal, analog signal, I have represented, which is a sinusoidal. So you can easily understand that the signal magnitude is varying with the time. So this is sinusoidal wave. It starts with zero reference, it goes to peak, comes back to zero, again goes to negative, comes back to zero, again goes to positive. This is how continuously it is varying with the time. That's why we say this is an analog signal. Analog signal, when you say, definitely it is a continuous signal. Why continuous? Because its magnitude is defined for all time t. So maybe it is human voice in the air, or analog devices will get the signal as an input for this, and output also. So this is varying with independent time t, right? So discrete signal, how it looks. Digital signal, discrete function of a discrete sampling variable with k integer. Vk is equal to v of t. This is mathematical, this one, nothing to worry. Nobody will ask you about no mathematical this one. Just I am trying to convey how signal information can be represented. Analog signal and digital. Digital, when you say, you have high this pulse and low, high and low, high and low. This continuously square wave, what we have no we are able to see here is no digital signal, right? Your computer, your CDs, DVDs, digital devices need a digital signal, right? Otherwise they don't understand analog. So these are the devices where you have to know, make sure that you convert it to digital and then feed the signal to these devices, right? So this is one more example of continuous signal and discrete signal. Actually, how you get the digital signal from analog, we call the process sampling. Sampling is the name of a process where you are converting analog signal into digital, but in between analog to discrete, you will get, then you make it a digital by assigning the values at a different instant of time. So that is a conversion process, we call it as a sampling. So sampling rate and all, it is out of scope here. Just we are trying to understand how signal can be represented. So analog and digital, or continuous and discrete, right? So discrete signal, same signal, when you represent from 0 to some value, the magnitude is increasing, and almost for last 3 values it is constant at 3, and t is equal to 3 and 4, 2 discrete no pulses you can see. So that represents the value of that signal, magnitude of that particular signal at that instant of time. So this is how you define or represent the signals. Okay, so this is just a basic idea for representing the signal. But now we are interested in main topic, that is number system. So number system, basically, we have we already know what are the number systems available for humans, what are the number systems available for computers. Computers, we don't use decimal, but we use decimal numbers. So 0 to 9 numbers we use to represent any number, right? Using 0 to 9 symbols or numbers, you can say. But what is the base of that, or radix? It is a 10. So decimal number, any decimal number, how you represent? With a base 10. With a base 10. If you say binary, binary means 2, base is 2. Base is 2. Octal means 8. So base is 8 for this number system. Number system, actually, it is a system which is used for representing number. That's it. That is a number system. And these are the common number system that we come across. Maybe when we use computer, we'll talk about binary, but what we give the data to the computer is decimal. When I type 20 in decimal, that converted binary is your computer is taking. So that conversion is happening. We call it as a encoding. At the end, again, when computer displays the value result at the end on the screen, we get again decimal values. That we call it as a decoding, coding, encoding and decoding process. I think you have come across, CPS you are studying, and you have come across these this kind of experience. What is that I am talking about number you feed. Suppose say you are trying to generate natural numbers from even numbers from 1 to 100. Suppose say even numbers, you are writing a program to generate even numbers. So how you are giving the number? Enter the number. When it asks on the screen, you write a printf statement, enter the numbers from 1 to 100. And then finally you put a condition just to check no even number you try to divide by 2, and remainder if it is 0, then you say no you say even number, right? So like that, you enter the numbers in decimal, correct? So for humans, which is useful, used by humans is decimal, correct? But computer won't understand it. But there is a device called encoder that does the job for you, that converts your decimal number into binary, and binary can be understandable by your computer. That's why I have shown the table here. Last two columns used by humans, used in computers. So decimal number, yes, used by humans, but it is not used in computers, right? Binary, second one, you can say it is not used by humans, only computers sake, because computer understands only zeros and ones, correct? Because it is a digital device, digital system that understands only zeros and one. And that's why binary, it is yes in computers, it is used in computers, right? But other things, here and there, you will understand the importance of these methods also, these number systems also. I will not go in detail. One by one, decimal to binary, binary to decimal, octal to binary, octal to decimal, decimal to octal, binary to octal, and hexadecimal finally. How we do the conversion? Okay, what are the different methods of converting these numbers? So that process we are trying to understand. So to begin with, let me say that this is how we represent the information. So elementary storage units inside computer are electronic switches actually. So electronic switches, maybe it is a transistor switch, what I am talking. So that works as a switch on and off and gives logical zeros and ones. That is what it is written here. Each switch holds one of the two states, on and off. That is, on state is logic 1 and off state is logic 0, right? So so we use a bit in binary, that is 0 and or 1, to represent the state, on or off. So two switches, what I have shown, electronic switches here. This says, no, dark line says it is an on switch. There is a path for the current flow. It gives the high logic. And this is an open switch. There is no path, right? So it is disconnected, off state. This switch is in off state, we call, right? So next, information representation, again for two no bits. Storage units can be grouped together to cater for large number range of numbers. Example, two switches to represent four values. One bit, two status, zeros and one, 0 and 1, and two switches to represent four values, right? When two switches at a time, they are in off state, the value we represent in binary, it is 0 0, correct? If first switch is off, second switch is on, value we write first off means it is 0, on means it is 1. So in the bracket, what is written on the right hand side, binary value 0 and 1. That is how you represent the switch status here, correct? Third point, third switch condition is on switch and off switch. So first switch is closed, second switch is off. So 1 0, you have represented 1 0 in binary. That equivalent decimal, if you want to see, that is 2, nothing but 2. 1 0 is 2, right? And 0 1 in binary is decimal 1, correct? So when both the switches are closed, both are in high state, how logically you represent the binary, how you represent in binary, it is 1 1. The binary state is 1 1. But what is the equivalent decimal value? It is 3. That is what written here. Just it is a information representation. How we do. In general, n bit can represent 2 to the power n different values. Correct? So if I have n value as 1, 2 to the power 1 is 2. Correct? So 1 bit can represent up to 2 values, correct? That is what written here. 1 bit represents up to 2 values, 0 or 1. 2 bits, if you take 4 values, just now we saw 4 cases of switches, right? 2 bits and 4 values, right? So 4 values, 0 0 1, second value is 0 1 1 0 and 1 1, correct? So if you have 3 bits, you can represent up to 8 values, right? From starting from 0 0 to 1 1 1. So this right? So 4 bit, if you have up to, you can 16 values you can represent. So right, 4 digit 0 0 0 0 to all 4 ones. So this 0 to 15, how you represent, right? So that is how no information representation can be described, right? So positional notations, let us discuss some positional notations. How we represent decimal numbers. Decimal number systems, the symbolically is 0 to 9 we use to represent, right? Position is very important. For example, one example you can take 7594. If you consider this number and it is in decimal system, right? Why decimal? Because its base is 10. If I represent base by 2, then it is a binary system. If I represent binary digits and no, at the end, if I write radix or base of that number as 2, then it is a binary system. If base is 8, it is a octal system. If it is base is 16, it is a hexadecimal number system. That you can understand very easily. Here one number in decimal. What is the number? 7594. 7594 in decimal. How you convert into in any form? If you want to convert, you can convert. If you want to convert into decimal, we can do that. Next slides I will show you. But here how we are representing it. So you have 4, 9, 5 and 7. So 4 is in which state? 0th position. What is the position of 4? It is 0. 9 is first position. 5 is second position and 7 is third position. So that's why 7 into 10 to the power 3 it is written, plus 5 into 10 to the power 2 it is written, right? So 9 is in first position, 9 into 10 to the power 1. Then 4 is in 0th position, right? So 4 into 10 to the power 0, correct? That is how you can represent a number, given number in decimal, right? In general, the same thing can be written in the expression form. So you can see here, same thing written, general expression. Okay. Similarly, 2.75, if I have a whole number as well as fraction, okay, floating number with the base 10, right? So decimal number you are trying to represent. So 2 is in 0th position, 2 into 10 to the power 0. That is how you represent 2. Plus, which position 7 is in? It is 0.7, means it is 10 to the power minus 1, right? So 7 into 10 to the power minus 1, 5 into plus 5 into 10 to the power minus 2, because it is 0.75. So 5 is in 10 to the power minus 2, right? Position. So same thing, for same thing, general expression can be written this way. So other number systems, we have no binary weights in powers of 2, you know, binary digits 0 and 1 we represent, already we know. Octal base 10, as I said in the beginning, octal digits from 0 to 7 we use. At the numbers, what we are using is 0 to 7 to represent octal numbers, right? So hexadecimal, where base is 16 and weights in power of 16, hexadecimal digits 0 to actually 50, but 0 to 9 we represent as usual, like in decimal, 0 to 9. Then from 10 to 15 we use alphabets A, B, C, D, E, F, capital A, capital B, capital C, D, and E and F, right? So A is 10 in hexa. For 10 you are representing by A, and B is for 11, C is for 12, D is for 13, E is for 14, and F is for 15. That is 0 to 15 is 16, base 16 hexadecimal number. That is what the number system you are studying here. So some conversion process, for an example, I have taken here, how you convert one form of number in one form to other. First example I have taken is binary number. What is a binary number? 1101.101. In binary, it is given. How you convert this into decimal? The title says base radix to decimal, base of this binary. It is in binary. Binary you are converting into decimal. Any number given, converting into decimal. So how you convert binary to decimal? This is a procedure, right? So first, whole number you take, fraction part you take later, integer part you take. So 1011 or 1101. So this one is in third position, because 0th position, one position, second and third. So 1 into 2 to the power 3. How I represent the first digit, binary digit? 1 into 2 to the power 3, right? Plus 1 into 2 to the power 2, plus 0 into 2 to the power 1. Since 0 into anything is 0, so I have not considered in the right hand side. Directly I have written 1 into 2 to the power 0. 0 into 2 to the power 1 I have not written here, as anything you multiply with 0 is 0. So directly it is eliminated here. So plus you represent the fraction part. So 0.1, how you represent? 1 into 2 to the power minus 1, right? So 0.1 is 1 by 10. 10 is 1 by 10 is 10 to the power minus 1. So here it is, since binary to decimal, you are representing 1 into 2 to the power minus 1, right? So plus 1 into 2 to the power minus 3. So just simplify, you get 1 into 2 to the power 3 as 8, 1 into 2 to the power 2 is as 4, and 1 into 2 to the power 0 is 1, 1 into 1 is 1. So 8 plus 4 plus 1 plus the fractional part, 1 into 2 to the power minus 1, that is half, right? And 1 into 2 to the power minus 3 is 0.125. So if you add, you are getting a number 13.625. That is decimal number. So this is a way how you convert a binary number into decimal. So this steps you have to show. Don't calculate with a calci in the exam. These steps are a must. Suppose this is a problem asked actually for 2 marks. Okay, binary to decimal. Okay, similarly, another number system you have octal. Octal to decimal you convert to decimal. So when you want to convert to decimal, simple, you have octal number system. So 5 into 8 to the power 2, 7 into 8 to the power 1, and 2 into 8 to the power 0. 0.6 it is. So 6 into 8 to the power minus 1, right? So that is what the representation is. Then you simplify this. 5 into 8 to the power 2 is what? 8 at the 64, 64 into 5, that is 320. 8 sevens are 56, 2 ones are 2, because 8 to the power 0 is 1, right? So 6 into 8 to the power minus 1 is 0.75. So if you add all, you will get the final answer as 378.75 in decimal. Similarly, any number you can convert into decimal. One more example you have is hexa. Hexa number is given 2a.8. How you represent hexa? A, B, C, D. Just now previous slides we saw, right? We saw the where is that number system? Yeah, hexa. Capital A, capital B, up to F we have seen, right? So A is 10, I said. So similarly, here the number given in hexa is 2a.8. Base 16 indicates it's a hexa number, right? So how you convert into decimal? It is 2. 2 is in first position and A is in 0th position. So 2 into 16 power 1. And A is 10. 10 into 16 power 0. Plus 0.8 it is in the problem given. 0.8. So 8 into 10, 16 power minus 1. So calculate, the final answer is 42.5. Similarly, any number given, maybe it is octal or base 5, also one example is shown, any base. If the base is 5, then it is a that particular number system, it indicates 16, it is a the base 16, that particular number system it indicates. Hexa we call, octal we call, but we don't use these last type one, because that's why. But you can convert looking at the base of the number, you can convert. So one more example, no, you can take up. Convert 10101 to the base 2. It is whatever I have written here, bracket outside 2 I have written, that is nothing but no, base 2 to decimal. Please convert this into decimal. 1010, sorry, I repeat, the problem you can take down is 10101. That binary number you convert into decimal. All of you just message me in chat. Give me answer for binary 10101. Yeah, see the chat window. You have to answer here. Yes, 21. Okay, so 21 in decimal, right? Next, convert 111.101 in base, convert into decimal. 111. Yes, others. Yes, convert these numbers to binary. Yes, convert the following decimal numbers into binary. Make it fast. 11. Okay, good. Others, make it fast. So answer is, okay, 17. Okay, good. Why answers are different? 4. Yes, yes. Yes. Yeah. Next, we'll go to decimal to binary conversion by these two methods we have, because this will be mentioned in the exam. What method you are following to convert decimal number to binary? Okay. So one method that we follow is repeated division by 2 method. A whole number, if it is whole number, if it is a fraction, we perform repeated multiplication by 2. Okay, so you have no division method for whole numbers, and no, for fraction number you have multiplication. So that is procedure, that is a method we use to convert decimal to binary. Let us take a few example, but before that, what is that you do, how exactly you keep the answer? Yes, these are the steps that you follow while performing this operation, decimal to binary. So first step, what you follow in successive division method is